Gravity is a force that pulls all objects together. Absolutely everything gets pulled towards one another. Now, if this is the case, which it is, if this were the case, why is Grandma not able to stick to the wall? Because the wall should pull on her, right? But Grandma in real life would fall. Why doesn't Grandma go flying towards the wall if gravity is a force that pulls all objects together? Any takers on that? Oh, nice to see. Good. Got a lot of you. All right, Case, if I call on, you're going to have to talk really loud. Why doesn't she fall at the wall? Why does she fall towards the ground instead?
The bigger the mass, the bigger the pull.
Bigger the mass, the bigger the pull. That's why you don't have to worry too much about opening your silverware drawer. When you open that, all those things don't come flying at you instantaneously because you have a relatively small mass. However, the Earth is the closest thing to us. It's got a large mass, so everything is pulled down more than it's pulled towards you. Now, if we start taking a look at some other things that have bigger masses, like let's take a look at the moon. The moon has a large mass, about 1/6 of the Earth. So why don't you go flying at the moon if you're taking a nice walk with your dog in the evening and the moon is out? I mean, that's terrifying if you really think about it. If anybody thinks you will be sucked up and killed by the moon at night, you have some major issues. But it doesn't happen. Why not? It's got a big mass, but you don't go flying at the moon. Lulu, why don't you go flying at the moon?
It's too far away.
It's too far away, which means that gravity is dependent on two things. It's dependent on the mass of an object. It's also dependent on the distance. Okay? So we're a nice, sweet distance away from the sun, where the sun has enough gravity to keep us in orbit, but not enough gravity to pull our little masses in towards it. So again, it's a balancing act between distance and mass. And later you're going to see it also velocity plays a little bit of a role. So it's dependent on both mass and distance. What we're going to do is we're going to get into a little bit of new material. So if you have your journal here, this will officially be Journal 3-3. 3-2 was the ELA journal. Okay? So again, if you're looking for a spot for that ELA journal, it should be Journal Entry 3-2 in your journal. I'll wait about 15 seconds or so for those of you who actually have brought your journal, okay, because you're prepared. For those of you who have not, you can go back and watch the video of this or copy somebody else's journal. But I would like to be starting soon. All right, this is a fun one, and it's kind of loud, and I wish I were a little closer to you right now because you can see this a little bit better, but I'm going to try to do a little demonstration up here, and it could get a little bit messy when I do it. So let's see what we got. This is a famous experiment that you're about to see. In fact, it's so famous it's almost like mythical at this point. So it is one of these experiments that tons of kids already know about coming to me. There's a famous experiment that a dude named Galileo Galilei ran hundreds of years ago on the Leaning Tower of Pisa. Does anybody know what he did at the Leaning Tower of Pisa? Some kids already know this before I start, so I might as well not teach something that you may already know. All I want you to do is explain what he did. Please do not tell me what you think the results of that experiment were. Okay, so again, just tell me what he did. What's going on?
He dropped one heavy ball and one light ball off the top of the Leaning Tower of Pisa.
Absolutely perfect. Okay? He thought a really interesting thing. He said, you know what? I'm going to climb to the top of the Leaning Tower of Pisa, and I am going to drop a heavy cannonball and a light cannonball. I'm going to see which one hits the ground first. Now, up to this point, most scientists believe that because gravity, if you have some perception of gravity at this time, heavier objects would fall faster than lighter objects. That's what most people believe. Dude named Aristotle believed that. A whole bunch of people, predominant folks at the time, believed that the heavy one will fall faster. And if you think about it, that does make a lot of sense. Galileo said, no, no, no. So what I've got here is I've got a golf ball, which I'm going to hold in my right hand. And I also have a ping pong ball that I'm going to hold in my left hand. You guys know from some experience with these that the mass of these two things are quite different from one another. Okay? If you were to hold them in your hand, one feels a lot heavier than the other. Okay? If I threw it at your head, you'd be able to tell that there's more mass in the golf ball than there is in the ping pong ball. So I can actually run this experiment up here in a very ghetto-rific way by simply dropping these two things on the stage. Okay? So I'm going to ask you a quick question by show of hands. If I drop these two things, ping pong ball, golf ball, I drop them both at the same time, at least as exact as I can possibly do it from up here. I'm not super coordinated. I don't have a mechanism to drop them at exactly the same time. Which one do you think will hit the ground first? And might as well call on some people because you got so many people with your hands in there. Which one do you think will hit the ground first and why? And we usually have a split decision. There are actually three different things that you could say. So I'm curious to see what those three possibilities are. Logan, what's one of the possibilities?
Neither of them will hit the ground first because they both fall at the same rate.
Good. They could fall at the exact same rate, a ping pong ball and a golf ball. Okay? Which is what Galileo thought might happen. He thinks that they will hit at the same time. What are some other possibilities of what could happen? Bradley?
Golf ball, like lands first and then the ping pong ball.
Good. Can I ask why the golf ball might hit the ground first?
Because it has a greater mass, so it would fall at like greater rate.
Yeah, and it might have more gravity, right? More gravity pushing it along or pulling it along, depending on how you look at it. Because we know the greater the greater the mass, the greater the pull. What's our third possibility? Third possibility, though it's weird and very rarely do I have kids choose this one. Samet, what's the third possibility? Great. Could anybody come up with a reason why the ping pong ball might hit first? I have a hard time with that. I can't see back there. Is that Lily?
Mm-hmm.
Yeah, Lily, what?
Because the ping pong ball is smaller, so it might go faster.
Oh, look at this. It is slightly smaller. You might know that off the top of your head. You might be able to tell from me. Hold on. It is slightly smaller. And maybe it's a little bit like more aerodynamic or something it might hit a little bit sooner. Yeah, what do you think, Carl?
I still think the golf ball hits sooner, but the ping pong ball could hit sooner because it's like less friction in the air.
Yeah, it might have a little less friction because it's smoother. And the golf ball has like dimples in it. You know what I'm talking about? If you were to, it's like rough. You can feel it along the outside. Yes, what's up?
Maybe the ping pong ball will hit first because it's lighter, and then gravity will pull it even more.
Yeah, actually, that's a really good point. Because Newton's second law says that if you put a force on an object, it will accelerate, and it depends on its mass. And if the mass is smaller, maybe gravity can move it more easily. So maybe there are some really good points. So here we go. You definitely want to check this one out. Best thing to do is simply listen. Okay? What you're going to notice, I'm going to do my best. Okay? They're not, well, let's just check it out and see what I can do here. Ready? Well, I know I'm going to drop both these. I'm going to lose them under the risers. You can't laugh at me. Oh, you can laugh at me for like 10 seconds, and then you have to stop laughing at me. All right, ready? One. You ready, Gia? I know you like laughing. Okay, here we go. Ready? 1, 2, 3. Wow, there was nothing to laugh at. That was pretty smooth. Come on now. All right. What happened? Just curious, was your eye quick enough to catch what happened? What happened there? What happened? I'm sorry? Yes, I did catch them, which was pretty good. How about the order in which they hit? You'd have to listen really carefully. Connor. It did sound like they hit at exactly the same time. And when Galileo ran his experiment, I'm just going to advance us through, he declared, you know what? These things will hit at the same time. And when he ran his experiment, he found that at precisely the same moment, both of these things hit. Now, really smart kids already start raising their hand and protesting this because of the statement he makes next. And here's something that you do need to write down. For falling rate, Galileo says that all, and that's the part that you might object to, and I'm curious to see what Samet wants to say because I know he's like itching to say something over there. Galileo says all objects on Earth accelerate at 9.8 meters per second squared regardless of their mass. The two cannonballs will hit the ground at the same time. The ping pong ball, golf ball, hit the ground at the exact same time. Regardless of mass. Everything accelerates at the same rate, and I even know the rate, that's what Galileo says, is 9.8 meters per second squared. People don't like this. and neither did some of you. You are disagreeing with Galileo. Galileo is considered the father of modern scientific thought, and Munger wants to disagree with him, which I find interesting. Great, I think you could disagree with Galileo here. So why don't you raise your hand and do it? If you disagree with this statement, raise your hand, but you're going to have to tell me why. You're going to have to give me a why or an example of something that maybe you could drop and they wouldn't hit the ground at the same time. So again, collecting a lot of hands here, which is good. The statement is, all objects on Earth accelerate at 9.8 meters per second squared, regardless of mass. Good, some of you don't like that. So for those of you who don't like it, I want to hear why. Is that Fitzpatrick over there? Let's hear it. Why don't you like this statement?
The air resistance will slow it down.
But it didn't slow these down. Can you, maybe this might be a good way to go. You're definitely onto something. I just want to build upon that. Can anybody think of any objects you could drop that wouldn't hit the ground at the same time? Just curious, can you think of any objects you could drop that would not hit the ground at the same time? Hamdia, what are you thinking? A piece of paper. And what would be the other object? A ball. So if I grab a piece of paper like this, and I grab this golf ball, you're telling me they're not going to hit the ground at the same time. You're telling me Galileo's wrong. That's what you're saying? That's a bold statement, my friend. All right, let's check them out. 1, 2, 3. I can tell you all know they're not going to hit the ground at the same time. And if I say why, you're going to be like, oh, the golf ball's going to fall, and the paper's going to go like this. It's like my little paper dance. That's a good dance. Come on, I like that. I use that every year. All right, so let's run it just for the heck of it, even though you know what's going to happen. 1, 2, 3. Okay, good. So now all of a sudden, Galileo seems completely wrong. Some kids will say, well, wait a minute, no, the ball's heavier. Doesn't matter that the ball's heavier. About 2 sheets of paper, and I make one of them into a ball. That was dramatic and took me a long time. All right, great. So these have the exact same mass. I'm dropping 1, 2, 3. Oh, the paper's still doing this thing. Fitzpatrick, I'm going back to you. Why does the paper do that? Why?
Because the paper is flat, because the paper is flat, there's more space for the air to push up on it.
Absolutely wonderfully stated. Galileo knows this, and wait till you see what I'm going to show you next. I'm going to show you a nice little cheap demonstration that will drive Galileo's point home. Galileo knows this too. He says all objects on Earth accelerate at 9.8 meters per second, regardless of mass. However, air resistance affects some objects more than others. So when you saw the balled up sheet of paper and the regular sheet of paper, you'll say, okay, that makes sense. They're going to accelerate the exact same rate, but the air resistance affects this paper more than this. All right, let's have some fun here. Now we got problems. All right, here we go. All right, so then let's choose something with similar air resistance. Fitzpatrick will say, well, this paper is like flat, and the air affects it more. Well, this is like flat, and the air would affect it just as much. So these things must hit the ground at the same time. If it's completely due to air resistance, correct? They will hit the ground at the exact same time, right?
Yeah.
No, you know this. You know if I drop these, don't miss it. 1, 2, 3. Yeah, you know that's going to happen. So Galileo says this. Galileo, oh no, you don't want the video to have you and your little comments in there. You want to make sure you keep yourself silent. If you got any questions, make sure you raise your hand and ask them. Galileo says, air resistance affects some objects more than others, but it's still going to be 9.8. For example, watch this one. Hands down, I know you want to talk, and that's cool. Watch this one. Galileo could run this at you and say, well, that still doesn't prove that everything accelerates at the same rate. It just shows us that the book hits first and paper. It looks like everything accelerates at different rates. How do you know it's only air resistance that affects it? We can do it, but this simple experiment, this one's tough for some kids to understand, but if you understand it, it's a nice way to drive home this point. If I take this book that has roughly the same amount of air resistance as this, and I place the paper on top of the book, okay, all it is set there, it's not stuck there or anything like that. It even hangs off the sides a little bit like that. I'm going to take this and I'm going to drop it, just like this, okay? Now, if you 100% believe with, or are with Galileo on this, and you believe what he's saying, then the book and the paper will hit the ground at the exact same time, because now the paper doesn't have any air resistance to deal with. However, if you disagree with Galileo, you think that the book is going to fall out from underneath the paper, then the paper is going to go like this. So you really need to think about that one, because I'm going to make you vote. You got to do one or the other. So look at this situation. I'm dropping this book. Either the book and the paper are going to hit the ground at the same time. The paper's going to follow the book right down. Galileo's completely 100% right. Or the book's going to fall out from underneath the paper because it's heavier, and then the paper is going to go like this. How many of you think that the book's going to fall out from underneath the paper and the paper's going to go like this? Everybody usually thinks that. Here, we only have about 2/3 of you, probably the other third of you is sleeping. Great. So it looks like 2/3 of you think the book's fallen out from underneath, and the paper's going to be left going like this for a few seconds and then hit the ground. Okay? The rest of you, the other third of you, are either sleeping or 100% with Galileo. So if Galileo's 100% right, paper follows the book. If he's wrong on this, then the paper comes flying off the book. Ready? Watch carefully. 1, 2, 3. Yeah. It followed it right to the ground. Now, you might say, well, no, it didn't. Well, sure, it caught the corners, but if you watch that fall, it was exactly the same acceleration the second you removed that air resistance out of the way. And Galileo wished he could go further, but unfortunately, he was dead about a couple hundred years before he could prove this experiment. Because if you could remove air altogether, then everything would fall at the same rate. I could take a hammer and a feather, drop them, if I could just remove the air. We can't suck the air out of this room and run that experiment. It'd be cool if we could, but we can't. We'd all be dead. Okay? So there is a place, however, where there is no atmosphere, and you can run this experiment. You can run this experiment on the moon. And during one of the lunar missions, this experiment was actually run. Do you know if we have audio set up? Did you set up audio or no?
I believe we do.
Okay, cool. We'll give it a try. If not,
Is it plugged in all right?
we'll definitely check it out.
Put it in.
Well, it's working.
Not putting it in.
No, that's fine. I got to be able to see this here. This always makes sense. Hopefully this is the right one. There we go. Always sounds like you're electrocuting yourself. Okay, so here we go. This is tough to see because this footage is older than I am. But you have to watch really carefully. There we got an astronaut. He's hanging out on the moon right now. In one hand, he's holding a hammer. In the other hand, he's got a feather. And he's holding them like this. If you watch really, really carefully, you're going to see Galileo's experiment being run hundreds of years after his death, with no air resistance in the way by having no atmosphere. Check out what happens. Again, you have to watch really carefully. In fact, it helps to squint your eyes, some kids say, to be able to see what's going on. So again, watch very carefully.
In my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. And the feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Mr. Joe.
I'm just curious, how many of you could see it? Could you see them actually hit? It's weird to watch the feather fall, because the feather would fall like this on Earth, but with no air in the way. Newton takes over, acceleration due to gravity, 9.8 meters per second on Earth, regardless of mass. The only thing is air resistance messes with some things more than others. At this point, we're going to dismiss you class by class. You all are going to go check the schedule. You have one more class on team before you're going anywhere. I'm going to go ahead and dismiss A first, so A can get going first. Rest of you, please take your seats. Stay in your seats.
Yeah, Dr. D is going to the flex room. He is going to the flex room.
Cool. B, you guys can go. Just look back and grab this.
Did you turn this off?